All right. Well, welcome everybody to our Fireside Chat today. My name is Jagdish Marani. I'm a Senior Product Marketing Manager in our Operational Databases team. And I have today with me Jonathan Katz, who is a Principal Product Manager for Amazon RDS Open Source. Jonathan, can you tell us a few things about yourself?
Sure. Well, thanks for the intro, Jag. I guess you know my name and title. One thing you may not know is I'm actually an active contributor to the Postgres community. I'm on the core team, which is generally responsible for governance, though the way the Postgres community works, everything is done by everyone. And I've been working with Postgres for a long time, first as an application developer, and then coming to the operations and the business side of things. So had quite a journey with it, and very excited to talk about these new capabilities in Postgres. Particularly around generative AI, machine learning, and everything that goes around it.
Great. All that is to say, we nailed the right guy for this fireside chat. So thank you, Jonathan. So generative AI is seeing an explosion of interest. Organizations are looking into generative AI for use cases like content generation, image, video, and music generation, art and design, drug discovery and chemistry, product and fashion design. I mean, you name it. The list goes on and on and on. There's almost no area that it doesn't touch. And Postgres and the pgvector extension fits into the generative AI solution space. So this should be an exciting talk for us today because it is so topical. Jonathan, let's start from the top. It can be confusing to jump into pgvector extension without a bit of background and context. So, how does an application user experience generative AI?
Yeah, that's a really good question. I mean, I think there's even a lot. There's so much to jump into here. Even like extension, pgvector, Postgres. But like, let's start from the application. And I definitely like I said, coming being an app developer at this point a long time ago, definitely a lot of empathy there. And the first place to start is like, what is prompting generative AI? No pun intended, as you'll see. I think the first thing I like to look at it as an app developer is the accessibility of the models. Like we're going to talk about all the different power these models have, but really the transformation in my mind is that it's so easy now to be able to get these expertise from these large language models and bring them to your application. So we can start with what a large language model is. And what it is that, imagine that, there's all this information out there, on the internet and encyclopedias, what have you. And if you're able to take a computer program and effectively learn on that information and then use it as a place to ask questions, that's effectively what a large language model is that it's done all this hard work of researching this very large corpus of information out there and brings it back to you as the user in a way where you can send it simple queries and it's able to give you, responses as if you're talking to another person. There's different ways to formulate large language models, and you see a lot of this going on right now with different things like Amazon's Titan large language model, and others out there. They all have different ways they've tweaked algorithms to be able to index and look over all this information, so that when someone or something comes in and presents a query, it's able to get a response as accurately as possible to what they're doing, or in some cases, you can churn things up to get it to, they like to call it hallucinations, but generate more creative responses, based upon the output, to help generate creative content. Now, Jag, what do you think about these large language models, from everything you've seen?
Well, I think it's great that you don't have to start from scratch. You've got a large language model to start with, and that definitely accelerates velocity. The issue is that they're so broad, right? They're very broad. They're trained on such a broad set of inputs that often what you get back isn't really what you intended to ask, and the context around what you get back is not appropriate or not correct. So that's the issue with large language models. So the question you get, the question you ask of it has to be very specific, and with the proper context around it. Otherwise, what you get back may not be relevant enough, right?
Yeah, and it's fascinating, right? Like we're seeing this new form of engineering come up, and again, I'm on the database side, so I don't see it as much directly, but this notion of prompt engineering, where a user might, come in and say like, what are some orange dresses that I can buy? And what's happening behind the scenes is that while it might look like a simple search query, the code behind the scenes like generates a prompt that says, find orange dresses, make sure there's no more than 10 results, look from, the following data sources, and it gets like very specific. So the LLM has this like very detailed prompt that it knows how to search over to try to return, the most appropriate results to the question that the user asks.
Yeah. The key is to ask a very specific question or augment the prompt with context to get better results. And I think an organization's internal data and their proprietary data is a good way to do that. Correct?
Yeah, and this is leading to a whole thing called retrieval augmented generation. It's a fascinating topic, and the example I like to give when I think about it is, let's say your brain is the LLM. So like take it like I'm an LLM. I'm nowhere close to as powerful as these LLMs, but I have some knowledge in there. And let's say I've learned a thing or two about critical care medicine through the years, either through osmosis, but primarily through my significantly better half's job being an ICU nurse. Now, a question may come to me about critical care medicine. I don't know why someone would ask me about it, but let's just say it happens. And I may not know the answer. So, what I do is I go to my significantly better half and ask her, and she likely knows the answer. And then I can return that to the person that asked me. That's how RAG works, basically. Retrieval augmented generation is that you reach out to an external source that has the additional information, and you're able to bring that into your own experience. So this is the power. Bring it back to the example you described, Jag. This is the power of being able to have your own proprietary data set and leverage an LLM to be able to deliver that experience to the user. Let's say you've collected information on. Let's say you're a real estate company and you've collected information on real estate listings, and for let's say they may not necessarily be public yet, you have that data set where a user can come in, query like, I want to find a house with 5 bedrooms and a fireplace located in the Seattle area. You take that query, you use some prompt engineering to go to the large language model, get the specific vector embedding you want, and use that as part of the similarity search to look through the different listings you already have in your database and return that to the user. Now, I just sneakily introduced a new concept into there in terms of the vector, and I think this is something we're going to dive well more into. But Jack, let me pause there. Is there anything you'd like to add on to that?
I think you left it in now, and you queued up the next question really well. Vectors are a key part of this, right? The search occurs on vectors, and similarity searches occur on vectors. So, just as a level set, let's talk about what vectors are. What is a vector?
Yeah, this is something I ask myself every day. But what's interesting is vectors are actually quite old. I mean, they've been around for hundreds of years. It's a well-studied mathematical concept. And in particular, if you go through an introductory computer science class, it's one of the first data structures you look at, from an array. And effectively, this is what a vector is. It's a list of things, but it has a specific definition. A vector, if you go by the mathematical definition, a vector is something that has magnitude and direction, but that doesn't necessarily mean anything here. In the context of generative AI, a vector is your mathematical representation of the object you're trying to index. So we see the example here, there's a vector for a cup of milk or a pinch of salt. I like to use my little cat friend here to say that if I needed a way to digitally represent the cat, I'm going to use a vector to do that. So that way, the LLMs are capturing certain properties of the cat so that we know what its mathematical representation ultimately is. That's the currency of the LLMs, by the way, it's the vector. And that's how we're able to determine if an object is, more similar or not to it. So let's take another example. I have, two very similarly looking bumpy balls on my desk. One is red, one is blue. If I were to search for them, you could tell that these are probably very similar. That I mean, they look, really the only difference is their color. I also have a football on my desk. And a football is a kind of ball, but it is slightly different from these two objects here. So the vector representations of all these three objects are going to be different, but we can use them to be able to search in terms of similarity. If I'm searching for outdoor sports or a football that I want to throw around, this is what we can use a vector to do to be able to determine what is most similar. So to recap, what is a vector? Aside from a mathematical object, It's the way that I can take whatever my query is, in a natural language or a video or an image, and be able to match it to everything I'm searching over in a way that I'm able to get the most similar results to what I want.
You know what really blows my mind is the number of properties you can have in a vector. I mean, uh, you can describe things down to very, very detailed and specific properties.
Oh yeah, it's wild. And I'll tell you a little secret, Jag. I actually studied machine learning in college, which, again, was a little bit of a scary long time ago. And, one thing that I looked at was, one thing that you looked at was, setting vectors. Those are the attributes of whatever you're trying to represent. And in my time, like a large vector was 20 dimensions, which even, still today, I'm like a 20-dimensional vector. What is that? I mean, here's 3 dimensions right here. This ball that I have on my desk, but what's 20 dimensions? I don't know. But you look at like these LLMs today, they're generating 1,500 dimensional vectors, 4,000 dimensional vectors, and like it still like blows my mind. Like, how are you able to represent all that information like that? And so as such, you need to make sure that there are ways to efficiently search over these vectors. And I think this is kind of both the fun and the challenge of dealing with this data is that when I'm looking for similar results, I need a way to be able to look at them efficiently.
So you can create clusters of these vectors based on similar properties, and I believe that's called a vector space.
Yeah.
And this is a huge simplification because it shows a two-dimensional vector space. Of course, with the technology we have, it goes way beyond 2 dimensions. But this is an illustration of how things would get clustered, right?
Yeah, exactly. And what's great about the two-dimensional example is that it starts breaking down as soon as you get to 3 dimensions in terms of the search properties. As I mentioned, like one of the keys to dealing with vectors is searching efficiently over them. And if you just have 2 dimensions, there's like a lot of little tricks you can do to be able to expedite that search. But as soon as you start going to like 3, 4, 20, 1,000, that's all out the window, and you have to look at different properties. But I mean, let's like zoom into this cluster a little bit further. I mean, you can see that presumably an LLM put this together, and it seems to have clustered things pretty well. Like dairy and cheese are kind of in the same cluster. Oat milk, it's not really milk, but you could see why it might be more similar to it. And going down the list down to berries, you can see that berries really are not related to dairy and cheese at all. Though maybe you have them in the morning or with a cheese board. So you can see why this is like a very nice way to represent our data because we can find different properties between them. And as we switch over it, the key is trying to see how far apart all these elements are. And this gets into the concept of distance. There's all sorts of different ways you can search for distance in vector space. And this is effectively how you're able to get in your search engine, results that are most similar. Probably the two most popular ones right now are Euclidean distance and cosine distance. So Euclidean distance is how far apart am I, line of sight. It's again something that's very easily understood. I'm looking at Jag right now through the camera. We're so far apart. And then there's angular distance, and angular distance is, or the cosine distance is like how far apart is my angle. So the angle between, say, this football and this cat.
Yeah, I think,
So
think Euclidean distance is something we're used to from high school algebra. The other cosine distance is a little bit more abstract for me.
yeah, it's funny. I was trying to think like, did we do cosine distance, in my math classes? I think the answer was yes. But what's interesting is that you're actually, particularly for some higher dimensional vectors, you're seeing some very good search results over them. And I think that's something we're going to talk a little bit more about as we progress through our chat today. But this is what it comes down to. If there's like one takeaway you have today about doing vector searches within databases, it's all about your distance operations and trying to make those calculations as quick as possible. And that's I think where a lot of both the fun and the challenge comes from today in our talk.
So, so we now know what vectors are. We know what a vector space is and how things get clustered together based on similar attributes or similar properties. Uh, the question remains: how do databases get populated with vectors, and then how do applications consume them? And I think there's a diagram that shows both ends of this. There's a batch process that essentially generates the vectors and populates the databases, and then an end user on the other side that's more of the transactional side where these vectors are getting used. So I think it's worth walking through this.
Yeah, no, that no, this is great, and I love this diagram. By the way, when I first saw this diagram, I'm like, this explains retrieval augmented generation in a nutshell. Why? So first, let's go to the right side of the diagram first, or the blue side of the diagram, where we have all this information that we've collected in some sort of data lake. So we want to be able to learn on it and create our appropriate initial training set based upon this information. Like this is all the business intelligence we've collected through the years. So we take that from the data lake, we put it into a data processing system, and we can use a foundational model or a large language model, such as Amazon Bedrock, to be able to create the embeddings from all that information. Then we can take those embeddings, or you might also call them tokens, and you can put them into your vector data storage system. So today, like when we look at the vector data storage system, we will be looking at Amazon Aurora and Amazon RDS, specifically the Postgres engines, because we're going to be using a Postgres extension called pgvector to store that. So let's recap so far. We have our data lake. We've extracted the information from the data lake and used an LLM to be able to turn all of this rich content of data into vectors and store them into our transactional system. Cool. So now we have the application. What happens with my generative AI application? I have a user come in and ask a question like, "Hey, how much does it cost to buy, this pack of, toddler-sized bumpy balls?" So, so the question comes in. The first thing we have to do is we have to take that natural text and we have to turn it into the appropriate vector embedding. And again, this is part of the prompt engineering that you might have, certain information you put into place to be able to wrap that question and bring it into your LLM. The LLM turns that into a vector embedding. Embedding is another term for vector that you often see in this field. Once you have that vector embedding, what you then do is you go to your vector database. In this case, it's going to be Amazon Aurora or Amazon RDS. You're going to perform a vector similarity search, which we're going to talk quite a bit about, in the coming slides. You find effectively the vectors that are most similar to the query that the user did, and hopefully it's going to pull out entries that are related to purchasing toddler-sized bumpy balls. After that, what you're going to do, you get the results back, and then you do a final. You basically go back to the LLM one more time to get the final natural language prompt. You return that to the user. So even though I spent a lot of time explaining it, the process is actually quite simple. To recap, your user asks a question, you send it to the LLM in order to get a vectorized representation of the question. You find the most similar results within your existing vector database. That's the retrieval augmented generation. You take the result that matches best, you bring it back to the large language model, which creates the final response, and then you send that response back to the user.
Cool. So, Jonathan, we've all experienced search for a long time. Most web applications have a field where you can put something in and do a search. So, how is this different from the search that we've all been using?
Yeah, that's a great question. And I think what's interesting is that this kind of search is more conversational. Typically, when you've done search in the past, it's a keyword-based search, and you put in a keyword, and you receive a whole host of answers. What you're seeing here is that with these large language models, is that you can sort of have you not sort of you can have a conversation with your search system, and you're seeing all sorts of applications come off of that. For instance, question and answer chatbots that can help you drill into more specific information about a topic. um, the other thing that we're seeing is the ability for content creation, typing in a simple little prompt and getting out a web application, for instance. And I think that's the big difference, is that interactivity and the ability to just generate a lot of content from very simple prompts. This is the difference between this generative AI search and keyword search we've seen to date. It's another way of doing a search. Like there's still a lot of benefits for keyword searches. I know I still do plenty of keyword searches every day, including researching information for our chat. So it's interesting to see what are going to be the different applications of both this generative AI work, as well as traditional keyword based work, because one, there's room for both of them, and two, like we're so early in terms of what we're doing with generative AI that I think everything that we can possibly do with it is only just beginning. Now, the the why Postgres is a good question, and I think it goes back. I mean, first, like if we step back and we look at Postgres and its history, it has been around for a long time. I mean, the first release of Postgres was back in 1986, as part of a UC Berkeley project, and it was open source in 1996. So there's been a lot of development on Postgres through the years, that making it a first class relational database. So we start with that. We take the fact that it's open source. There's a vibrant developer community, which I'm grateful that while I'm not directly a developer on Postgres, I'm grateful to be a part of that community. And it's the ability to see how much is able to work with workloads at particular scale, particularly relational workloads. We've seen there's all sorts of features that help with rapidly processing queries, allowing for custom data types, indexing, and really one of the most powerful things about Postgres is its extensibility. Now, Postgres is open source, which means at any given time, someone can come in, fork the database, make a new database, and slap their own name on it, and continue to work on it. And that's great. You can do that to help solve specific problems, but you don't necessarily have to. Postgres has something in it called extensions, or an extension framework that lets you add functionality to Postgres without forking it. And that's a really powerful concept because you can load extensions into Postgres, add new things like data types, indexing methods. You can even add functionality that lets you communicate to other databases. It's incredibly powerful, and both Amazon Aurora and Amazon RDS support over 90 extensions in Postgres today. So we take that, we take all the rich functionality already within Postgres, and suddenly like you can see where we're building up to be able to store the vectors from these generative AI workloads in it. One nice thing about keeping your vector data next to the data you're using for your generative AI applications is proximity. Exactly that. That I know that if I have my vectors in here and the data I'm trying to represent right next to it, it's one less step to be able to return that information to the user. You can also, this also lets you, continue to add application data that's ultimately vectorized, and you'll be able to work with it all within one space. And the nice thing is there's a rich tooling ecosystem around Postgres. Client drivers, ORMs, other things that app developers love to build with, that just work with the pgvector extension that we're going to talk a bit more about today. So it's very convenient to keep your vectors all in one place. Whether you're using Postgres or another system like OpenSearch, because it's convenient. That convenience makes it simpler for you to develop and rapidly iterate on your applications. Yeah, and it's great that you have choice. One thing I always liked about when I was on the application developer side is having choice of being able to use the correct tool for the correct problem. Excuse me. Postgres is great as a Swiss Army knife. It does a little bit of everything. It's very strong on the relational side of workloads. It has these awesome data types that make it simple to develop applications. And as I said earlier, you can just keep extending it, adding more data types, index types, etc. And there's sometimes where it makes more sense to use another system like Amazon OpenSearch service to be able to augment what your application is doing. It's something that I've done throughout my career, that I would combine multiple data sources or database systems to be able to solve specific problems with them. And the great thing is they can all work together with the appropriate integration logic. So it's nice. The good thing about having choice is that you can use the right tool to solve the right problem that you're looking at. And it's great that there's ways to have all of these different databases work together.
Great. So I've got my database populated with vectors. How often do I refresh that, update it? Uh, the data keeps changing. So, is it important for me to continuously be changing it, or what are your thoughts on that?
Yeah, I mean, I think it depends. I mean, I've seen all sorts of, talking to customers, I've seen all sorts of different workloads. There's some customers that do, a bulk load of their data for retrieval augmented generation, so they only need to, vectorize it once, and then they go ahead and attach their Gen AI app to it, and and that's fine. It's indexed once, and they don't have to do that much work thereafter. There's some that are, continuously updating it. Typically, what I've seen is that it's an insert-only workload. They may add, say, 100 vectors a minute, and it keeps adding to the index, and they're able to do the appropriate searches on it. I haven't seen as many that are updating it. That tends to be less frequently happening, but there's certainly workloads where that happens. And based upon your workload, this is where the idea of vector search becomes very interesting because there are different search techniques you may want to use in order to optimize the retrieval of it. And I think this is where we're going to start diving into vector search because the challenge with vector searching is it's exhaustive. It's hard. Imagine, when you're searching over like a point in two-dimensional space, you basically have to make two comparisons, your x coordinate, the y coordinate. Well, what about, finding the distance between a 1500 dimensional vector? You really have to look at every single dimension of those 1500 dimensions in order to determine like how far apart you are. Like you can't just, necessarily shortcut it and like look at like the first three and say like, okay, this vector is closer to this vector. So we need to have certain search and indexing techniques available to be able to speed up our these searches. Otherwise, if let's say I have 10 million vectors in a table and I need to find the five most similar vectors, looking through all 10 million vectors every single time is very, very, very exhausting. Yeah, I think, what's nice about extensions too is that it allows a way to do rapid iteration while waiting for upstream. And what do I mean by that? So one of the hallmarks of Postgres is its stability. It does release its software once a year. Actually, the Postgres 16 release is coming up in September. And you know that once something is in Postgres, it's been battle tested and stable and it's ready to go. Extensions can have a different release cycle. They can release more rapidly. You can use it to test out different concepts. And it gives a way to be able to try things before they make it into upstream Postgres. And this is a path that has happened for several different data types and other innovations in Postgres. Postgres has a full text search engine in it. Did you know that?
Oh,
And the thing was the full text search engine actually started out as an extension first, and it was iterated on, and then it was brought into the core project. So this is the great thing about extensions is that it lets you test things out before bringing it into the core project. Now we had a long talk about vectors at PGCon 2023, which is the big Postgres hacker summer that occurs around May or June in every year, and there definitely was a lot of excitement for allowing for Postgres to support the vector data type. But part of the thought process around it was, well, let's see what happens with the on-disk storage format or these different indexing techniques, because before we bring in something that's going to have some level of permanence, we want to have it as a well understood problem. Now, there's a little bit of a misnomer there because Postgres has actually supported vectors since the beginning. Postgres has an array data type. It actually premiered with the UC Berkeley release, back in the 80s, and it actually was there as an optimization for looking up access control privileges within the database, so you didn't have to go to multiple tables. Now, while this vector data type is, oh sorry, while the array data type is quite awesome, you can actually have arrays of effectively any type that's stored in Postgres. It doesn't actually have any of the functionality required to be able to do indexing or the appropriate distance operations on those data types. Postgres then added, surprise, an extension called the cube extension that did add all of that, both indexing operations and the ability to do the distance calculations on different vectors, but it only supported it up to 100 dimensions, which, while I was in college, would have worked just fine. But in this world of 4,000 dimensional vectors, that the 100 dimensional limit is a little low. So this is where having a vibrant open source community helps because when we see these emerging workloads and these emerging patterns, one, we can work on them and we can work on them very openly to help try to set standards around them. But also, we can do it in a way that doesn't is not necessarily gated by Postgres, once a year release. And this is where the extension is a very powerful concept.
it's great. So, I mean, it's been brewing since the 1980s. The core capability's been there, but there were some technology triggers recently, and we've seen the hockey puck adoption curves and things like that. So, that was a combination of market pull as well as the technology triggers that made it all possible. Um, and that curve is pretty astounding in terms of the PG vector, adoption. Um,
Yeah.
do extensions in general, or the PG vector extension in particularly, inherit all the benefits and capabilities of Postgres?
Yes, because you're in Postgres, you inherit from Postgres, but there are some things to be considerate of there. So the first thing that pgvector does is it provides a vector data type. And that's easy enough to plug into the Postgres storage system. So you get all the benefits of Postgres, that you see below. The different, scale operations, and probably most critical, the durability operations, making sure that when you write a vector to disk, it gets stored to disk, it's safe, you're not going to lose data. There's appropriate crash recovery in place to make sure that the information as written is stored there. But then, there's this notion of indexing, being able to efficiently look up the vectors. And again, this is where Postgres is awesome in its extensibility, is that it has an interface for you to define your own indexing. So Postgres comes with standard database indexing known as a B tree. It's something that if you're not familiar with, you've probably used it if you're running a relational database. And some other custom index types that actually that are actually quite powerful. So there's the gist index, which actually you can perform this vector similarity search with the gist index, though currently it only supports up to 3 or 4 dimensions. The gin index, which is used in the full text search system, a Brin index or a min-max index, which actually I believe Postgres was the first database to have that implementation, and others as well. But if none of those are able to solve your problem, or you're not able to build your data type to use one of those indexes, Postgres does have this low-level index creation interface called the index access method interface. And from there, you're responsible for a lot of the implementation in terms of how do you vacuum or clean up the index, how do you store the data to disk, how do you scan the index to look up your value. But what's cool is that you can do that, and to me, that's what's awesome about it, is that you can have something like a pgvector implement some of these well-researched vector indexes and do it outside of upstream Postgres, but yet still be able to help allow people to use Postgres to store this data.
It's great, and from what I've seen, it doesn't take a lot to add vectors to Postgres. In fact, I think uh, we've talked about this, right? Why use Postgres for vector searches? Anything else you'd add to that?
Yeah, yeah, I think the first bullet point I think is really important, and again it's something that speaks to me from my previous days as an app developer. Is whenever I adopt a new technology, or whenever considering I considered adopting a new technology, I wanted to just work. Like, especially if it worked with things that I already had in place, it just made it so much simpler to adopt. And granted, I would add in new things into my tech stack, even if it meant writing new code or learning a new system, particularly if it solved a problem. But if I could just like drop something in and it worked with my existing tech stack and it gave me, X amount of more capabilities, cool. I love that. You can't dismiss the easiness of being able to take in something new without having to do much work. But yeah, I mean, it's great that Postgres can be there as like your source of truth of all of your vector data. Like, I think that's a wonderful opportunity for many of these applications.
Absolutely. I mean, if there's something new and exciting, add it to something that I already know, right? And a lot of people already know Postgres. I mean, it's the adoption is absolutely awesome.
Yeah.
So adding it to Postgres versus asking developers to learn something completely different is uh, you know adding it to Postgres is the way to go.
Yeah.
Um, and adding it to Postgres is not a huge lift, right? Uh, tell me what it takes.
Well, adding the extension or adding the vector search capabilities, because I have to say, writing an extension can be a little bit of a lift, but once, thanks to the work of the PG Vector community, it's very easy for you to add the vector capabilities to your database. Effectively, you can provision a Aurora or RDS Postgres instance and just run create extension PG Vector, and boom, you have a vector database. Actually, there's a typo there. It's create extension vector, but maybe we can take the pen on it and just cross out the PG part. But yeah, no, it's very easy. And again, any of the Postgres extensions that are available on RDS or Aurora, typically you just have to run create extension, the name of the extension. In some cases, you might need to modify your shared preload library setting, and each extension might have some additional capabilities. But in general, it's very easy to just expand your Postgres capabilities within your database. I do want to call out Trusted Language Extensions, which is an open source project that we had announced at reInvent in 2022. And it's a way to help bring your own extensions, your own software packages, and run them on Aurora or RDS or anywhere that you have pgtle installed. Personally, like, I love it. It was actually a problem that I used to have to deal with back in my app developer days where I'd have all these stored procedures all over the place, and I wasn't necessarily sure like which version of them I was running in any given place. But I could, with the trusted language extensions, I could wrap them in, this software package. I could give it a version, and then I know exactly, what version of the code I'm running, in any given place. The nice thing is they're also written in what we call trusted languages in Postgres, which have certain security properties. So you know that you can't escalate to a privileged account that you don't have access to, or make remote external networking calls. So it's a way to help iterate for developers to iterate faster and be able to expand the capabilities. Now, pgvector itself is not a trusted language extension. It's written in C, but in part because pgvector is really focused on not just the storage of vectors in Postgres, but the performance aspect. Yeah, so I think so. We've been talking about pgvector, but it's time to drill into what it actually is. And the
Sure.
first thing is, as Jack mentioned, it's open source and it's designed to just store and search over billions of vectors. And there's different ways that you can get to billions of vectors, all sorts of different techniques with partitioning or where you store them. But the idea is that is the foundational tool for being able to store and search vectors in Postgres. So today it also provides an indexing method. So imagine again you have a million 1500 dimensional vectors in your database. To search for your 10 most similar vectors every single time is going to be exhaustive. Like you don't want to have to scan a million rows every single time. So you need some kind of indexing. And IVF flat is a method for performing this indexing, which we'll go a little bit more into depth in terms of what that is. But the other thing when you do these similarity searches is that you have to choose your distance metric. And it could be Euclidean distance or LT distance, like we discussed. There's also cosine distance, which is very popular, and inner product distance. With IVFI in particular, you basically have a couple ways to tune performance and recall. And when you're talking about these kinds of vector searches, you can't talk about them without discussing performance and recall. So let's go back to the example of not using an index. If I scan like all 1 million vectors in my database, that's called an exact nearest neighbor search because I know, I've looked at every single vector. I know exactly what my, 5 most similar vectors are. In order to optimize this for indexing, you can't look at every single vector. So this is called an approximate nearest neighbor search because you're hoping that you're getting the answers back that are most similar to what you want, but you may not see the entire, you don't see the entire search space, so you might not get what's called 100% recall, or basically making sure that you've seen all the vectors in the data set that are applicable to your search. So performance is great, recall is great. Well, having a good performance, a good recall is really the goal of all of these approximate nearest neighbor systems. And the way that IVF flat works is that it chunks each vector or breaks up your vector set into a number of lists, which you can choose. So if I have a million vectors, I might have 100 lists, which would ultimately divide the vectors into, let's see if I do my math quickly. It's 10,000 vectors per list. I think that's the number. And you do that so that way you don't have to search, over the entire set. Now, you don't just want to randomly divide those vectors among the list. You want to find lists that are most similar. So what happens is that you calculate all the different centers within your vector set using something like a k-means algorithm. And the idea is then if you find 100 centers that are able to relatively evenly distribute the lists, you're then able to look through your 1 million vectors, assign them to the closest center within the list. And the idea is that all these vectors are the most similar to each other. Conceptually, it's not as complicated as some of the other algorithms out there. And what's great is that it's very quick to build this index, again, compared to some of the other algorithms. Now, here's where performance and recall comes in. Let's say I do a search, and I say, okay, search only through one list for my 10 most similar vectors to my query vector. You can go into that list and you'll get those 10 vectors very quickly, but this is where you have to consider recall because based upon how you calculate your k-means, you might not have all of your most similar vectors within that list. So you might need to go visit more lists in order to improve your recall. But naturally, as you start visiting more lists, your performance is going to go down because you have to make comparisons against different vectors. So this is where choosing the right number of lists and choosing the right number of probes will help dictate the performance and recall using the IVF flat indexing method. And this is part. This is going back to my application developer days. This is where you have to start getting a little bit of database expertise, or at least a little bit more SQL expertise to be able to figure out what's the best way to tune it. In some ways, we're all going to become folks who tune machine learning algorithms.
All right, I'll prepare myself for it. Um,
Yeah,
so there are some performance recall trade-offs that you have to be aware of and make the right decisions in terms of lists visited and things like that. Um, uh, you also mentioned that the next point in the chart, it's available with all the existing client libraries. So it's, whatever library you happen to be using, you can continue using that library and benefit from pgvector. And this is an example that you can walk us through, Jonathan.
yeah, sure. So the idea is that with pgvector, it's when you're using it, it looks just like any other SQL you're writing in Postgres. You can create a table. In this table, we're storing chats in this table. We can give it a unique identifier. You have the content of your chat, and then an embedding that's associated with it. So let's say you load, 500,000 rows into it. Then the next thing you do is you create an index. In this case, I used, if you look at that line that says embeddings vector cosine ops, this is basically saying I'm going to use a cosine cosine distance search over it. In this case, I chose the list number of 500. That's following the upstream guidance, in terms of list building. But again, choose the number of lists that makes the most sense. Then when you write the SQL query, it looks just like any other SQL you write. You're selecting data from your table. The way that you unlock the k nearest neighbor or the similarity search is in your order by clause. So what you're going to say is, I want to find the distance between embeddings and my query vector, and then your limit is your k. With your limit, you're going to say, in this case, find my five closest vectors. So it should feel very natural, and that's part of the point is that when what pgvector helps you to do within your Aurora and RDS databases is that it gives you the vector similarity search in a way that should feel very similar to writing any other SQL query in your system.
Yeah, and obviously the limit has a performance implication. So don't ask for the sky because it's going to take a lot of cycles to get it, um, right? And depending on what you're doing, maybe the first few is enough. I hear you have a demo for us.
So the rumors are true. So let's see how it goes. All right, so I have my screen ready. Um, so what I'm doing today for the demo is I'm using a Jupyter notebook. Uh, I kind of wish I got more familiar with Jupyter back in the days when I was experimenting with machine learning models, at least professionally, because it's great. You can basically run through examples directly from within the notebook. And what we're going to do today is we're going to build a chatbot, or we're at least going to visualize building a chatbot. So we're going to scroll down. What I did is that I did set a few things up ahead of time. Let me just make sure everything is still running. Yep, it looks good. And what I'm going to do is I'm going to initialize a few things in order to build out my LLM, and then I'm going to talk through what we're doing here today. Let's see. Okay. So what is all this code that I just went through? I don't want to speed through it. So one of the most popular frameworks for being able to build generative AI applications is LangChain. Because LangChain pulls together a lot of the essential tooling that you need, including interfaces to the large language models themselves, interfaces to vector stores such as pgvector, and the interactive components that you need in order to do prompt engineering and build out the chat applications. So in the beginning of this example, which I'm going to speed through, we basically built a chatbot from the Amazon Titan LLM. So we can see, let's just chat with it real quick, see what happens. Hello. I'm going to think a minute. It's like, oh, hey, I'd like to talk about myself and learn new things. What would you like to know? Uh, do you think this chat is going? So what's really cool here is that we with like very little code, like we already have like an interactive chatbot. This is pretty cool in my book, and we can tell it to quit and say, hey, we're done with the chat. We do different things to like add personality to the chat. Part of this is configuring the LLM, but I want to skip ahead to get to chatting with context, because this is the idea of retrieval augmented generation. that I have a corpus of information that's going to enhance the chat. It could be from my, the data I've collected through the years of my application. It could be something new that I'm starting up where I'm taking, some of the data I've collected and I'm building it into my chat. So the first thing we're going to do is we're going to put together a database that has everything that we need to get started. And in my database, as you can see, it's an Amazon Aurora database that's using pgvector, and LangChain provides the appropriate connection components to be able to integrate pgvector directly into your application. So again, this gets back to the developer tooling aspect. If we have the developer tooling available, it makes it much simpler to build the application. Now, the next step, which is going to take a little bit of time, is that we need to build some embedding. So I'm going to start building that out while I explain this code. We want to build a Q&A bot that's going to give us answers about Amazon SageMaker. So Amazon SageMaker is one of the ML services that we have here at AWS, and it has a wonderful FAQ for frequently asked questions about how the service works. So I took that FAQ, it's in a CSV format, and we're basically going to be learning against it we're going to generate embeddings based upon the data via Amazon Bedrock, specifically the Titan LLM. So it looks like we took that, we've generated vectors, and now it's in our database. So here here's a quick test of that. And we see, here we go. Yep, we have it in the database, and everything looks like it's working. So now we can build our chatbot. So again, we're using LangChain to help us with this because LangChain has all of these nice wrappers that can help expedite our development. So in this case, we're creating a prompt template specifically geared towards asking questions around Amazon SageMaker that our chatbot now knows, and we're gonna keep information about it in memory. This is a way to make sure that our chatbot knows how much of the conversation we've had, so it's not necessarily giving us the same answer all the time. So finally, we're ready to have a chat. And of course, I forgot to run the previous step. Eventually, generative AI will make sure that you click all the steps in your demo before you go ahead with it. All right, so we're ready to chat. Let's start. All right, so let's ask, what is Amazon SageMaker? Just thinking, and here we go. Here is a phrase, directly from the FAQ. Maybe with some modifications here. And what's great is that, with very little work, I can just import an existing data set and create a generative AI application. Now, in an actual generative AI application, you probably won't be using a Jupyter notebook, that you're going to distribute to your customers. You're going to make something that's a little bit more, like this. And this is an example of a generative AI application we built using the Amazon Aurora FAQ, where we could have a full conversation with a chatbot and tell us all this wonderful information about Amazon Aurora. This uses the Streamlit framework, which again, another thing that I wish I had when I was an app developer, because it makes it super easy to build these nice applications, and you can integrate it with LangChain to be able to get the full this full generative AI application experience. So that's my demo today. Tell me how you think I did, Jag.
Great. I think you did great. You got me interested in, using this kind of capability. Certainly much more engaging and better than wading through documentation. And think of the number of domains that you can do this for, right? I mean, it's a whole new way of discovering things and understanding things, learning things. So, yeah, I think this is, I can see how it would be game changing for a number of different areas. So, absolutely.
Yeah,
So, Jonathan, this is not a static area, right? That things are always improving. We're working on it. Open source community is working on it. Uh, can we take a quick look at what's coming?
of course. And this is
Mhm.
what's exciting about open source is that you can see what's coming, even before it's been released. At least if you like to read through the Git commit logs. And
So,
there's a lot of exciting things coming to pgvector. And I think what's most exciting about it is this focus on performance. That if pgvector to date was about making Postgres a functionally viable vector database, now it's hitting the turbo button on it. And there's a few things on the actually I'm excited about everything on this list, but In particular, I'm very excited about speeding up the IVF flat index build times. There's the ability to build the indexes using parallelism, and in a lot of tests we saw like a 2 to 4x build time improvement. IVF flat itself is already a pretty quick method, so anything to make it faster is even better. Speaking of, we've seen in some of the we've seen optimizations to distance calculations, particularly on Graviton. We're seeing a 2x faster performance on particularly the building operations, and that's going to be coming in the upcoming pgvector release. Also, other things too, being able to do sum aggregates, summing up vectors, is useful in a lot of the mathematical operations that occur, and support for the native binary format from Java for the Java adapter. So previously, in order to use the Java adapter to communicate between your Java application and your Postgres database, it would take your binary formatted vector, convert it to text, send it over the wire to Postgres, then take that text, convert it back to binary, and perform the operation. And there's a little bit of overhead with that. So being able to stream it natively in binary reduces that overhead. And some of the testing, we saw a 30% performance improvement in bulk loading by using this new formatting technique. And finally, the one that I'm most excited for, which is not coming soon now, it's actually committed to pgvector, and I'm looking forward to when it's ultimately released and available, is HNSW indexing. HNSW indexing stands for Hierarchical Navigable Small Worlds. And it is really a state of the art vector indexing method because it answers the question of how can we get good performance and good recall, without sacrificing either of the two. Uh, the way the algorithm works is that whenever it tries to add a new vector to the index, it searches like some portion of the vector space around it and tries to pick out which are my most similar vectors, and then it makes connections to a subset of those vectors. So you're always pointing to whatever vectors you're closest to. So that way, when you perform a search and you find some set of vectors you're closest to, you're looking around this neighborhood, the n in HNSW, and more likely than not, you're finding the vectors that you're most similar to. One innovation that HNSW adds into is the layering of the search, and that's the hierarchical part. That you first search a space where that's fairly sparse, there's not that many vectors, and then you drill down further and further and further into the space, into this denser space. So by the time you're at the bottom layer, you're around your neighborhood of vectors that you're most similar to. Again, that's to help optimize for performance. HNSW is implemented by a lot of different systems, including OpenSearch, and we're excited that it's coming to Postgres. And early tests show that the implementation is really awesome. That we're getting much better performance recall, and it's great too for the data sets you're talking about, Jag, where you have to continuously add vectors to them. HNSW is well suited for that. So super excited for this. It's a long time coming in many ways. And by a long time coming, I mean 3 months since pgvector was available on Aurora and RDS. But
Yeah.
it's going. No, I think it's going to help a lot. And the nice thing too, is that it does work with the IVF flat index, where you can have a partition set of vectors, and each partition uses an HNSW index. And then on top of it, you use an IVF flat index to be able to determine what partition your vector goes into. So it acts as a coarse quantizer there. So it's pretty cool, like mini tools.
For those who want to know more about the HNSW indexing, you wrote a blog post on this, correct?
I did, yeah. It was an early look at it, and again, this is moving so fast. We'll see, how well that blog post holds, a few weeks from now. But yeah, it was to compare it and like baseline it against IVF flat and other HNSW implementations, just to see how it compares and see where it makes sense to use. And this is again where you always have to look at performance and recall because IVF flat can actually outperform HNSW, but it's doing that at a lower recall level. And HNSW is able to get better performance with higher recall, much sooner in your searches. There's other things to look at too. I always like to look at index build time. I mean, this is always something that was the bane of my existence when I was managing databases, and before Postgres had the ability to do something called create an index concurrently, which lets you to continue writing to a table while the index builds. But index build time, it's something you gotta pay attention to. And IVF flat is a much faster index build method than HNSW. But again, there's the trade-off. The trade-off is I can get a better performance to recall ratio, which HNSW. So you have to pick where you want to be able to spend more time.
Great. And this is all imminent stuff. I mean, it's like next release of the extension.
Correct.
You know, and HNSW indexing may already be there, as you said. So,
Yeah.
uh,
Yeah,
yeah.
that's committed. This is all expected in pgvector 0.5.0 release. So whenever you watch this video, like it may already be out. So what's exciting is that while it may be coming soon when we're recording this, like this is, as you said, like the release is imminent. We're looking forward to it. And again, it may already be out.
Mhm. And there is a longer term roadmap as well, right?
Yeah, and I think, this is where, I always be careful when I talk about open source roadmaps because they're aspirational instead of prescriptive. Like these are all things that we're working with the different communities in terms of implementing, and some may make it in, some may not, all may make it in, all may not. But this is how, we see the projects going in their different ways. And the first is focusing on upstream Postgres, and what can we do there to continue to support vector workloads. Currently, there's actually a patch to add vector functionality to that array data type we talked about in Postgres. And while that might not bring indexing per se, it at least would bring the various distance operations to be able to work with your data already stored in Postgres arrays. We're also looking at ways to better support parallel query, in a way that could help pgvector, and also what things we can do to help extension developers building different kinds of vector indexing, regardless if it's pgvector or other extensions, to be able to fully leverage the power that's within Postgres. With pgvector, what's on the roadmap? Product quantization. Product quantization is a technique that can help reduce the amount of storage a vector takes up on disk, but also increase performance, and also help you support higher dimensional vectors, uh, particularly in indexes. It's a very powerful technique, but like all techniques, it has trade-offs. When you reduce the size of your vector, you need to be mindful of recall in your searches. So that you might need to do more work in the search in order to be able to get higher recall. So definitely excited for that technique, though. Like we've seen some other systems implement it with like great success, and I'm definitely optimistic in terms of what pgvector will do there. Other things we're looking at, the name of the game is speed, as you can see from those other entries. Where can we parallelize things? Where can we add support for parallel query? What other operations can we parallelize? What can we leverage from hardware acceleration? pgvector already contains a lot of great tooling for auto vectorization of functions. So leveraging SIMD instructions, say in graviton chips. This allows us to perform vector calculations more quickly, but there's definitely still more that we can unlock there, and I'm excited for what the future holds, in that area.
Fantastic. A high velocity open source community. Lots going on, right?
Yeah, indeed.
Mhm. We knew that we were going to run long here and not have time for questions because we covered so much ground. There was so much to cover, and we anticipated kind of the need for extra time to answer questions. So we have a Q&A question, the Q&A session, especially for this. It's on Thursday, September 21st, 8 a.m. Pacific time. And the entire purpose of that session is Q&A. So your questions answered, and we'll dedicate an hour to just answering your questions. So thank you all very much for listening in today. Jonathan, thank you so much. Your expertise here has been great, and you've dug in deep into something that people want to understand. So I'll keep coming back to you for more. Thank you very much. All right.
Thanks, Jag. It was a great interviewer. So you did an awesome job, and definitely happy to chat more about this.
Yeah. I learn as I go, and I'm finding this to be really exciting.
Cool.
All right. Thank you very much.